Okay. Again, thank you for being here for this lecture. We can see here lecture number 1, vectors, norms, fundamental properties. Therefore, we can justify somehow that this slide is a little bit old in the sense, because we are speaking about a background. Let me start with the definition, the formal definition. Please pay attention. A point in an n-dimensional space can be denoted by an n-tuple of real numbers. And then we have an example. I mean, I put here formally what I wrote in the first part of the definition. A capitalized equals parentheses A1, comma, A2, A3, comma, AI, comma, dot, 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 AN, parentheses. A, please pay attention, is called an n-dimensional vector. AI are scalars. Interesting. First of all, what is the definition? Definition, the word definition came from Latin. Means if you analyze the word, define. We have also a verb to define, and the substantive is definition. This means to limit. This means to give some, let me say, boundary to a concept. Which concept we are considering here? A point. Of course, this is a possible definition. This is a possible definition. It's not the unique one. This means something interesting. Yeah, because if it's just a possible definition of a point, it could be that the point is not clear in its content. Because if I have more than one possible definitions, strange. It could be that these definitions, excuse me, say different things. This is a little bit a philosophical question. We will see how mathematics, is close to philosophy. We will see. The goal of this course is also to understand a little bit better the sense of definition, propositions, properties, theorems, and so on, even though we didn't demonstrate many theorems, because as I told you, engineering mathematics is applied mathematics. This means we try to demonstrate a couple of theorems in order to do some exercise also in the context of the demonstrations. But basically, we try to apply, therefore, engineering. Coming back to this definition, again, for a concept, we have in math, but also in philosophy, possible different definitions. Now, the reason is, as I told you, to define the verb, the action. The verb is an action. The substantive is definition. It's something which limit the concept. Why we have to limit it? To understand. I don't want to say better, but to understand. Because better is a little bit strange, because they have a different definitions. What is the best definition? I don't want to go in depth on these philosophical aspects, but in any case, because we need to understand, or to be able to communicate what we intend with the word point, we need to limit this concept here. We need a definition. This means it could be that the definition leaves outside its limit something which sometimes could be useful. In the sense, the definition help to understand, But in other situations, it could be that is not possible with this definition to understand because could be useful to consider aspects of this concept with this definition does not consider. I don't know if this is at the beginning of our course to speak about the philosophical sense of the definition can help. But we will see in this course, I will insist a lot of the sense of a definition, why we use this definition, and then properties and so on. Nevertheless, let me go ahead. I think doing some exercise in the sense trying to work with this definition, probably we can understand also better what I intend. It seems that with this definition, that point, at least in this context, a point is a vector. Please pay attention. A point in an n-dimensional space. Of course, now we have it to be clear, but what is an n-dimensional space? It seems to be that this definition needs other definitions. Of course, but anyway, I decided to start with this definition for practical reason. I don't have really much time to do a course which includes every aspect of mathematics. The reason is we are here for engineering mathematics. This means, of course, I try to do my best, but of course here, in order to start with the point, the definition is unclear what is an n-dimensional space. This means the definition does not tell exactly what the point is. But please recall a little bit what you know from Math 1, from Math 2, assuming that we know intuitively what is dimensional space is. Basically, I would like nevertheless to tell you, we can see intuitively what a dimensional a dimensional space is if you look at this mathematical expression. And nevertheless, I tried here to put can be denoted by an n-tuple. Now, the question is, what is an n-tuple? Is this? It's clear because of real number. Exactly this expression here, which somehow defines also an n-dimensional space. Because an n-dimensional space, please pay attention to the words, can be denoted by an n-tuple of real numbers. Another goal of this course is more than Math 1, Math 2, and so on. And to give you the idea that mathematics, let me say, is a language. Not only because 1 plus 1, we use symbols, or A, capitalize, equals, but is a language in the strict sense of the word. Because this equation here, let me say equation is not so equality or identity. Anyway, this expression, in general, this expression, we can understand better. A capitalize, if I read this expression, A capitalize equals parenthesis, A1, comma. You can see, you can hear in a sentence. I can write also this sentence, which is a subject. The subject is A capitalized. We have a verb, equals, and so on. Therefore, believe me, at the end of this course, the goal, I hope, but I always achieve this goal. The student understands very well how mathematics is easy because it's not much different to learn a language, in the sense a new language. Of course, some part of the course, I think, I try to tell you something new, of course. It's new. The program is new. But what is new is the approach with respect to the mathematics. The engineer typically try to be not so abstract, even though the concept starts from abstract idea, a point. Yeah, basically it seems to be from this definition that the point in an n-dimensional space is or equals a vector. Because about the vector we learn also in high school. No? Here is a vector with n dimension. This means with n scalars, characterized by, let me say, n components. Yeah, here I tried in the last part of the slide a little bit to clarify what I didn't define exactly. Excuse me, I have to stop 1 second. I come back. Let me see if I am able to pause. I hope. Yeah, 1 second, I come back. Yeah, I am back. In this remark, I put a little bit an explanation without considering the formal definition, which I wrote that the set of all n-dimensional vectors is called the n space, or a vector space of n doubles of real numbers. In some books, this is exactly the definition of an n-dimensional space. For the notation, I would like to say that we can indicate this n-dimensional space by R. We can see up to n. R is the real, let me say, domain, but with n dimension. This means up to n as a way to represent. Don't be scared from math. If I am able to also clarify the nomenclature, the notations, believe me, it's not difficult. At the end, we have another remark at the end of the slide. Very important, each definition, even though sometimes I write just if isn't a condition, but each definition is always if and only if. The reason is, as I told you, define means to limit. This means, what is the meaning of if and only if? This means that the condition holds in both directions. I try to clarify. Look at this definition. I say that the point equals a vector. At the end, how I can translate this complex information which I have in this definition? A point is a vector, or a point equals a vector. The same. If I say a vector, I intend the point. But it's also in the other direction, as I told you now. And a point is a vector, but the vector is also a point. This means that the definition holds in both directions. The sentence A equals vector is equivalent to say vector equals A. With A. Very important. In the concept of the define, close, works in both directions. Again, A equals vector, but I can say vector equals A. even though sometimes I write just if, no? But inside the definition, we fix the concept clearly in both directions. Okay, let me go ahead. We have a couple exercise which can be used also as an exam exercise, but of course I try to put in the exam exercise something more challenging, even though based on this properties. Let me show you these three. Um, uh, here I classify as definition. Excuse me, I made mistakes. We have another definition or definitions, basically three definitions to be precise. I copy from a book, they say definitions one, but anyway, we have three definitions to be precise. Definition number one, equality. We can see here that a vector A or a point A, if I say vector, as I told you before, I intend point. If I say point, I intend vector. I intend vector. A equals B, point A equals B, or vector A equal B, means, look, we have an arrow in both directions. Exactly if and only if. This means if A equals B, this means that each component of A, which I indicate from the first definition, A not capitalized, equals all element of B, each element of B. Better to say the corresponding element of B for each I. No? Basically, each component must be equal. And in the other direction, if all components are equal, we have the same point. This means equality. Isn't a definition. Isn't a definition. This means we know now what we intend if I say that we have 2 points, but these 2 points coincide in one. A equal B. Addition. A plus B equals C means this definition is constructive, which helps also the first one, because the first one helps us to say when 2 points or 2 vectors are equal. The second allows to build an algebra. Algebra means calculations. This means A plus B equals C means that I have to sum all corresponding component of A with B equals the results. Basically means the vector C is a resulting vector which considers the sum of each corresponding component, but also vice versa. If I sum all corresponding components of the vector A and B, I have another vector C, which is the sum of both. Multiplication by a scalar, as another definition, I try to accelerate a little bit because you know, B equals A alpha multiply A, which alpha is in a scalar, not in a real scalar, means that all element of vector A, components of A, are multiplied by the scalar alpha. And this is B, Bi for each I, which define the vector B capitalized, which is the vector A multiplied by alpha. Yeah, here we have some example which is extremely easy to be understood. No? If A12, B12, of course, A equal B for the definition of equality. A plus B is trivial. I will add the corresponding components. 1 plus 1 equal 2, 2 plus 2 equal 4. I don't need to insist here. And also the last exercise, alpha multiply B. For instance, no, alpha multiply B. In the definition, we have alpha multiply A, but it does not matter. Is exactly if A equal 1, 2, we have that here we have an error. I think, no, it's okay. Everything's okay. Alpha multiply B is alpha, the first component, and the second component, 2 alpha. As it's clear that in accordance with the definition, I have to multiply by alpha each component of the vector. Now, ready with the definitions, we will see some properties, meaning of this. With this limitation, with this possible algebra, with this possible algebra, we can derive some properties that can help, let me say, to speed up possible calculations, to improve in the sense to build the structure for a more, let me say, structured algebra. It's easy. Commutative property, A plus B equal B plus A. How I can demonstrate? I mean, let me clarify a little bit better. The definitions, I don't need to demonstrate the definition. Because it's something, as I told you at the beginning, so the definitions are structures which allow to build our language. In the sense, at the beginning, I have to clarify what I intend with the word point. Or let me see here, a little bit easier probably here. What I intend if A vector or point equals B. The definition is exactly what I intend. This means I can fix basically whatever I want. I can use also different definition of equality, of course. I can say that not AI equal BI, the corresponding component, but the first component of a vector with the last one, the second component with the before last one. We have a different algebra. I mean, A and B here are equal in accordance with this definition. But if the definition is different, and the definition is, for instance, A and B is equal if the first component equals the last one, the first component of A equal the last component of B, and the last component of A equal the first component of B, these two vectors are not equal in accordance with the definition. This means depends we defined the equality, depends on how we define the addition, depends on we define the multiplication. We generate another algebra. Now the question is, but here is everything is arbitrary. If I define another way, I have different results, different language. It is. Just 1 second, in order to clarify this concept here. We will see next week. At the end of this session, well, almost at the end, we will see here, page 19. If I ask you, how many circles did you see? It's interesting, no? The question. Do you see the picture, no? Yeah. We have a black geometric form, we have a green geometric form, and we have a red geometric form. If I ask you, how many circles are visible? Typically, please pay attention. The cleverest answer is always, as always, it depends. This is always the cleverest. In particular, when we are speaking about math, also philosophy, it depends. Basically, and then we come back on my lecture at the beginning. We will see this in detail. I would like to answer how we can. It depends, of course. It's always almost valid answer. In this case, it's really interesting. It depends because it depends how we define the norm. In fact, we can see different types of norms. in order to understand what I intend, depending of the definition of the norm, we will see next week. We, I can show you basically that we have three cycles because we have, if we define three different norms, we have the possibility to see three cycles in correspondence of three different norms. In order to understand from today, that depends what we intend. In this case, with the term norms, distance. Norm is distance. And then we can visualize, let me say, different cycles in accordance with three different definitions of distance. Let me come back on this, what I told you. But anyway, this is interesting in order to motivate you to follow me, I hope. If I define a different way also the sum a plus b, if I define, for instance, the first component with the last one with the first component, the result is not a plus b, is not 2, 4, no? First component 2, second component 4. If I define the first with the last with the first, we have 3 here instead of 2. Yeah. And we have, instead of 4, we have 3 again. What is correct? Both. Both in the sense what you see here and what I told you, using a different definition of the sum. The student asked me about, okay, but with this, what I have to use? Both. Depends what you have to, which kind of problem you have to solve. It's interesting, this last sentence, because for engineers it's extremely interesting, this aspect, because but this means that the problems could be, because also the problems need to be defined. I mean, basically, we don't have problems. We don't have problems because depends what of the definition of the problems. I mean, if I don't define the problem, I don't have problem. It seems to be a little bit strange, but think about that a little bit. It's strongly philosophical based. Also in our life, no? But anyway, about the life I don't want to speak. But mathematically, we can see that depending on the definition, we have different results. But result of what? Very often we say we solve this problem, and this is the result. But we will see in this course, I will try to define problems for a given definition of the problem. For a given definition of a problem, I would like to repeat, we can use different definition in order to solve this specific problem. You can realize from this first hour that I try to go in depth in the philosophy of the math. We will see that for the exam we need also calculations. We need also really. Also in this hour, half hour more or less, the first half hour of the hour, we have seen nevertheless important concept of math. Because math, believe me, is not only 1 plus 1. 1 plus 1 is just the result of a possible definition of a sum. Here, with this example, we can understand very well, if I define a different way, the results are totally different. The question, we are confused, because if the solution depends on the definition, the solution is not valid. In fact, the solution is not valid. The solution is related to the problem. This means at this moment, I didn't define any problem. We will see in the future that, for instance, this possible definition is very useful for solving such kind of problems, but not all problems. This slide that I put now on these 3 cycles. Let me say 3 cycles. I will come back. I think next week we have 4 hours, 2 blocks. I will be able to complete this session. we will see how we can define different distances, and this means the concept of the circle is not uniquely connected to the circle which we learned at school. I have here a glass, no? It seems to be that's in a circle. Is in a circle depending of the distance which I can define. Now question, but why I have to define different concept of cycle? Depending on the problem which I have. At this moment, try to have in mind this my sentence, depending of the problem which I have. But it seems to be that everything is arbitrarily, no? Auf Deutsch willkürlich. It is. But also that the problems we generate selves problems, our problem. In the life, I don't, I'm sure. But in math, yes. In engineering, yes. And then if I am able to, if we define the problem because we want to solve, because we realize that could be useful to solve this problem defined in this form, of course, now we understand why we need appropriate definition to solve this problem. Okay, we will see with some example a little bit later, but this is a little bit the character of this course. To go really in depth on the concept, but of course, we need at the end to do calculations because sometimes students don't love math because they say, oh, this calculation is boring. Is really is boring. I have to say it's boring. But if you see a little bit more in depth, math is extremely interesting in the sense. I try to give you this feeling. Look at this. Properties. Properties must be demonstrated because the properties depend on the definition. Different definition, different properties. Look at this, A plus B equal B plus A. We have learned also in, I think, high school, or probably also in elementary school, commutative. This means I can commutate, I can invert the order of the element in a sum. How I can demonstrate? I have to consider two general vectors, A and B, characterized by A1, A2, dot, AN. I do the same for B, B1, B2, Bn, and then I can demonstrate that I can invert. It's easy to do that. I don't do because it's too boring. You haven't seen probably in other courses. Yeah, associative. A parenthesis, B plus C parenthesis equal A plus B, A parenthesis, A plus B parenthesis plus C, and so on. Also, this can be demonstrated for a generic vector A, B, C, as I told you before, in accordance again with the definition of the sum. I don't need to do it. Distributive is the same. In accordance with the sum in accordance with the definition number 3, believe me, it's extremely easy. It's extremely easy that the left part equals the right part. And that means the property 3 is also demonstrated. The idea is to use the definition to demonstrate some properties. Meaning, why is it useful to have some properties? Because I can use directly, in the sense it's just useful to have properties because I can use directly without doing the calculations, no? Somehow. Associative, I can do the same. The idea is to show you in general that in accordance with definitions, but this property, very important to understand, holds for the definition which I gave you. For different definition, it could be that not all properties will hold. Now, left equal right in general can be demonstrated using, as I told you, using the definition. And also the property number 5. Very important properties must be demonstrated. Property. Interesting this remark. Look here, in the last expression, this plus here is not exactly this plus here. Just to remark, because this plus is a plus between scalar, this plus here and a plus between vectors. Just to remark. Just to understand, but just a remark. Yeah, you know that, no? The vector 0 is the identity element of addition. This means if I add 0 to A to B, I don't change the vectors, you know, from elementary school. And we can see here the negative vector is of a point is in a point such that A minus A equals 0. Just to recall this let me say property, like let me say 0 multiply A equals 0 and A multiply A equal A. We can see basically that the 0 is the vector, no? Is the neutral element for the sum, and 1 is the neutral element of the multiplication. This means exactly so. The calculations which we have here is a calculation which is sometimes is I mean, states a new notation of a vector. I mean, the vector A minus B sometimes is indicated AB over line, and the vector A minus 0, which equals A, is indicated A0 over line, just to put a new notation, let me say notation. Again, in the book, I will tell you which kind of book I used. The name is the author I remember well, Apostol. I think geometry, something like that. I will tell you exactly the book next time. But you don't need to buy the book. Absolutely, is enough if you come to the lecture. The second group of definitions in the book is written definitions too. Basically, we have all the three definitions. We can see that we have now two vectors, vectors A and vectors B. Look, the definition number one second. This three definition is extremely important. We will see also next time, also in the first part of the course, because these three definitions are related, I would like to say, to the concept of directions. In fact, the definition one, we say that A and B, two vectors. Very important now, we are speaking about vectors because if you speak about points equals vectors, it seems to be quite abstract, the direction of a point. But if points equal vectors, we can understand at least in terms of vectors. We have two vectors, A and B. We say that they have the same direction if, please, in definition, if means if and only if. I will repeat again what the meaning. Let me say, if exists alpha, I didn't put what alpha is in the scalar, in this sense positive, because I am considering the same direction, with B equals alpha A. But means also if B equal alpha A with alpha positive, A and B have the same direction. Again, the definition goes in both directions. Excuse me. In this case, we are using the word direction with different meaning. In the definition, direction means the direction of the vectors. When I say that in the definition, the word or the sentence holds in both directions means in the sense of implication. Again, I can say A and B have the same direction if exists alpha positive with B equals alpha A. But I can say, because it's in a definition, if B equal alpha A with alpha positive, the vector A and B have the same direction. Definition 2. Basically, these two vectors have the opposite direction if exists alpha negative with B equals alpha A. And also, this sentence can be read also in the inverse way. B equal alpha A with alpha negative states two vectors with opposite directions. Again, the definition can be read from left to right, or from right to from right to left. Just to understand that inside the definition we have always if and only if and only if. Sentence number 3, or the definition number 3. Two vectors A and B are parallel if exists alpha not zero with B equals alpha A. And also, I can read the sentence in the other direction. I don't read now. Interesting consideration. It seems that the parallelism concept, A, B, include both. Because two vectors, A and B, they are parallel, could have the same direction, but could have also the opposite direction. In the sense, include both. We can read also from the definition, because it is enough that alpha not zero. This means could be two parallel vectors, A and B could be with the same direction, but could be also with opposite direction. This means the definition of parallelism, let me say, includes definition 1, definition 2, if you want. Look at this now. Probably you heard about the dot product. In our specific case, in a dot product, which is in a particular form of inner or scalar product. At this moment in this slide, we are speaking about dot product. Therefore, I put inside parentheses, inner or scalar. But of course, as I told you, the dot product is in a particular form of inner, or if you want, scalar product. Let me look at this definition. We are speaking about a dot product. But again, the dot product is in a particular form of inner or scalar product. But inner or scalar product, which is in a way to define the product, we can say inner or scalar, is more general. The dot product is in a particular form. It's the form which you see in the middle of the slide. The dot product between any vector A and B, which belong to R up to n dimension vectors, remember at the beginning, is defined as exactly what I wrote at the beginning, in the middle of the slide. A dot B, we read A dot B equals, okay, this means that the sum from 1 to n is the dimension, n is the dimension of the sum of the product of the corresponding elements of the vectors. This means, nevertheless, something interesting, because it seems that the dimension of A must be equal to the dimension of B, but nevertheless, is almost clear from here. Anyway, the dimension n must be for A, must be for B, the same. It's almost clear from A, comma B, which belongs to R up to n. But I would like to underline also this concept here. Given this definition, I have here 4 properties. I didn't write properties because I don't want to use a lot of nomenclature or, yeah. But anyway, they are 4 properties, because we should demonstrate that A dot B equals B dot A. How we can do that? As I told you before, I consider a general A which n component, I consider general B with n component. I will show you that left equal right. Believe me, it's just boring to do that. I don't want to do that because it's extremely boring. But it works for this, very important to notice, for this possible definition. Believe me, if the definition is different, could not necessarily it works. Distributive property. They say, I have to demonstrate that the left equal right for this definition. Homogeneity, extremely interesting. Alpha which multiply A dot B equal alpha multiply A dot B equals A multiply A dot alpha B. This means I can, let me say, consider different combination. It can be also demonstrated using the general A and general B. Alpha I didn't specify, but again, as before, I specified before, is in scalar. Is in scalar. Positivity A dot A larger or equal 0 equals if and only if A equals 0. If we don't have, if the components are all 0. If all components are 0, A is equal to 0. We have seen this before. This is easy to demonstrate because basically if you look at the definition, the equation in the middle of the slide, we have basically the sum of what A1 squared plus A2 squared plus AI or AN squared. This means in any case it's positive, but could be 0 if all element is 0. All element of A, the components of the vector. Okay, let me show you this. This is an interesting theorem. For this theorem, we will see that I try to tell you about the demonstration. As I told you during the course, I will insist just a little bit on the demonstration, but in some cases could be important to show you at least how we can demonstrate some theorems. Even though engineers very often, as I told you, don't need to demonstrate, even though in my papers, in my work, in my research work, I demonstrate also some theorems. Therefore, I decided to include in the course also some theorems in order to understand, in order to have an idea also how the engineers work. I don't know if I have it here. I will tell you next time in some papers of mine, even though I'm an engineer, I have theorems, I have properties. I demonstrate this. Even though for engineers it's more important to apply. Therefore, in the course I will consider really, I think, just a couple of demonstrations. One of them is this one. Cauchy-Schwarz inequality. Theorem, again, definition I don't need to demonstrate. I can define theoretically what I want. Of course, should be useful to solve the problem, or should be useful to build some properties which help to solve some problems. Theorems are like property, a little bit more stronger. We put more in evidence something which theoretically is more important than properties, results, which can directly used to solve some problems. About the problems, I didn't tell you. We will see during the semester. I didn't define any problem. Theorem. For any vector, A and B, basically we have two vectors. No? Any means any A, any B. Belong to R up to N. R up to N I already defined. Now the nomenclature is clear. No? This n-dimensional space. Then this is the result, which must be demonstrated because I can say I don't believe that A dot B square less or equal. The symbol here, we have a signal. So before I didn't tell you about this. No? This means less or equal. Less or equal means not more. No? A dot A, please pay attention here. Multiply B dot B. I would like to emphasize when I say multiply. The reason is, I don't remember if I forgot to say, that A dot B, I don't say, but it's clear. If it's defined as the sum of the product of the corresponding component, it's a scalar. It's a scalar. A dot B is a scalar. Therefore, here I would like to emphasize that A dot A multiply B dot B. I have to say multiply because A dot A is a scalar. B dot B is a scalar. This means a scalar multiply not a scalar. Of course, if I say dot is not wrong because theoretically I can define also the dot between two scalars. Why that? Because the product of two scalars. Because if the dot is the sum of the product of all component of the vector, two scalars are two vectors in one dimension. The scalar is also a vector in one dimension. Or I can write formally this expression here, in this form here, applying the definition. Apply the definition of A dot B and apply the definition of A dot A, we can see here. Apply the definition of B dot B. The equality holds if and only if A and B are parallel. Let me show you a little bit. Let me show you a little bit the proof. It seems to be complex. No? For any vector, hold this or equivalently this. Here, from here to here, I apply just the definition of the dot. Please pay attention here. Assuming A not zero and B not zero, the reason is if A equal B equals zero, the theorem hold in the sense of trivial form, in the trivial form. Let me show you. Is this enough? The demonstration, this sentence here is a little bit too strong, but is this enough? I mean, the sentence holds. The sentence must be demonstrated if A not zero or B not zero. If one of both are zero, is zero, excuse me, if one of both is zero, of course is valid, no? Because we have a zero here, less or equal zero. This means I have to consider both vector A and B not zero, otherwise holds. It's trivial. Huh? If B equals zero, we have a zero, less equal zero. If A is zero, we have again zero, less or equal zero. Clear. I would like to improve a little bit here. The case interesting? The case interesting, but it's not so totally ununderstandable. I think we can understand. I have to consider that A not zero and B not zero. Look at this now. If I consider a vector C as a combination of A and B through X and Y, we can see here, with X and Y scalars, with X and Y, excuse me, with X and Y, I probably have an error here, no? With X and Y scalar. It probably is a LaTeX error. X and Y are scalar. And let me consider this combination. C is also general because A and B, whatever, X and Y, no hypothesis of X and Y. This means C is a general vector, but I can consider, for instance, this. We will see why this position. Let me consider this. I don't have any restriction of X and Y. This means I can consider X equals B dot B, because B dot B is in a scalar, and Y equals A dot B. Now, assuming this, then we will discuss these assumptions, because why I am considering this element here. Now, if I write C dot C, in accordance with this consideration or this assumption, I will write this. Easy. At this moment, don't care about why I am considering C in this form. Just to remark that C is a general vector. C is the general vector, Y A is the general vector, B is the general vector, X and Y are general scalar, and I choose this general scalar using the general vector B and the general vector A. Everything is general. I don't know if it's clear that. I don't have a restriction about C. This in order to emphasize the sense. A is general. It doesn't matter which one. I can consider A1, A2, A3, and so on. The same for B. X and Y, here I have to improve this. With X and Y scalar, this with X and Y is a LaTeX problem. You know LaTeX probably a little bit. It's just a repetition of the software which I used to generate the slides. X and Y are general because B and I are general. Now, C dot C, clearly this one. Now, if you consider the distributive property, which I quickly explained before, but also without considering this, it's intuitive to see that I can write, nevertheless, I apply the distributive property with the dot, with respect to the dot. We have x squared, x in a scalar, which multiply A dot A. I told you quickly about this property, but believe me, it's intuitive also from the knowledge which we have. I can do the same for the dot with B. We see x squared multiply A dot A. We can see in the same way y squared multiply B dot B, because I can distribute also this YB in this element here. And then if you remember, we have here 2 times xy, which multiply A dot B. Again, I simplified everything, but probably you learn in gymnasium this distribution here. I told you before that this distribution holds also for vectors. I mean, from here to here, look at the properties before, or otherwise intuitively, we have also something similar in the algebra of the binomial product. Now, look at this. If you remember the position of x, which is here, we have b dot b squared, because x is b dot b. In the same way, I can write that y squared is a dot b squared because of this position, which multiply for b dot b squared a dot a, for a b squared b dot b, because it's written here. No? And I can do the same here. If I plug in x as here, if I plug in y as here, I have exactly this. Then, do you remember? Here, everything is in scalar. Element is in scalar. This is in scalar. There are 3 elements, scalars. But I can simplify in the sense I can subtract, or I can algebraically sum this and this, clearly. Applying the commutation property of the, we have this scalar here, which multiply B and B. We have a B and B which multiply the same scalar. Easy, intuitive. This means from this line to this line, absolutely clear what I am doing. Now, I can put in evidence, we can see here, b dot b, because we have a b dot b square, b dot b here. Again, they are scalar. This means I put in evidence b dot b. I have a b dot b here, remains, multiply a dot a minus a dot b square. Now, why this positive or zero? Is positive or zero, this sentence, we read positive of zero. This means, yeah, exactly more than zero, no? Strictly more than zero. More than zero. More or equal zero, excuse me. Because C dot C is positive or zero. Is zero if C is of all component of C are zero. Do you remember this? This was here. Instead of A, I have C, but C dot C is positive or zero. Zero if and only if all elements of C, in our case, are zero. This means until here, we understood what we are doing, at least the calculations. Now, what I'm doing here, B dot B is always positive. Because C dot C, I told you exactly now. This means this is necessarily positive because C dot C is positive. This means that this element inside the bracket must respect this condition. This means that this element here must be less or equals B dot B multiply B dot A dot A. And this is exactly what we want to demonstrate. Look at here, in this form or in this form. Now, at the end of this demonstration, we have just a remark, but at the end of this demonstration, we can see how the mathematician work. The mathematician work putting a general expression, and a general expression, totally general, C is totally general, X and Y are totally general, and then using the positiveness of C and the property which I already told you here, to demonstrate the sense which I want to demonstrate. Now the question is, but how I can think to define the element C? This is the difficult job. But the inspiration is exactly this sentence here, which is basically this, no? Because you can see that A dot A multiply B dot B minus A dot B squared must be positive. Must be positive. This means the inspiration is to generate a vector, a scalar, using a vector. The scalar must be positive. This means C dot C is the vector which I need as a general combination of the element A and B, general combination, but general combination means that X and Y should be general. And the result is just a function, or this expression is just, let me say, a function of A and B. This means X and Y must be general and must be a function on A and B. Of course, this is a little bit advanced mathematics in the sense of theorem, and in fact, it's a very famous theorem, Cauchy-Schwarz. Let me conclude for today, considering the last sentence, no? Equal if and only if A and B are parallel. We can see from here. I don't know if can be understood, but I will try to clarify. B dot B cannot be zero, because we assume that B is not zero. Do you remember at the beginning? Yeah. Now, when is zero? When this here inside is zero, right? But this means that C is 0. If I write here 0 equal this one, it's exactly our case. 0 equal this one is exactly our case. This means C equals 0. But if C equals 0, we have XA equals YB, which is exactly what we want to demonstrate. A equals Y divided X, which is a scalar, It doesn't matter if it's positive or negative. For the parallelism, it does not matter. Multiply B. Multiply B. Now, here is useless, this sentence, because I told you that A and B must not be 0. If A and B are not 0, is also X and Y not 0. This means I can omit this. But if you remember the definition of a parallelism, two vectors A and B are parallel if, as definition means if and only if, no? A equals alpha B with alpha not 0. This is alpha, definitively not 0. Because Y is not 0, X cannot be 0. X, do you remember, is D dot B. Okay, we can stop here for today in these 2 minutes. Try to do at home. Let me see. I have two vectors. 1, 2, 3, 0, 1, 1. What about V1 dot V2? In accordance with the definition which I told you. It's easy to remember, no? 1, 2, 3, 0, 1, 1. No? Another example. V3, 0, 0, 1, V4, 1, 0, 0. If you want, you can write, or again, the problem is the same. In accordance to the definition, I give you an idea. This multiply this is 0, plus this multiply this is 2, plus this multiply this is 3. This means 2 plus 3, 5. Try to do at home this. I don't know if it's clear. The definition is the sum of the corresponding components. 1 multiply 0 is this, plus 2 multiply 1 is 2, plus 3 multiply 1. Everything is 5. Try to do this. We will see next week that these two vectors have particulars because they are orthogonal. We will see that the dot product equals 0. Orthogonal. We will see next week. If you have a question, you can question me. I have time for you. We are exactly 45. Otherwise, next week again, just online. Just online. We will conclude with this session, and we will see how these three geometrical forms can be circles. All these three geometrical, let me say, set the forms as you want. Okay, if you have question about the content or about the course, but we will have time to speak about the examination. This could be also two possible, a little bit more complex, but two possible exam exercise for the topic, vectors, points, something like that. In a couple of weeks, I will also upload an exam for last year or something like that. So we can see which kind. But in the lecture, I will do exam exercise. Basically, also this easy, but I will start with easy exam exercise, and then we will in the exam we can find different exercise with different difficulties in the sense. Questions about definition, theorems on? If no, next week, just per Zoom again, the same time, we have 4 hours, 2 blocks next week. Okay, let me see in chat if somebody asked me something. Yeah, I stop immediately.